In this video, we're going to see how we can combine continuous functions to create new continuous functions. This is going to be very helpful because we can start with a short list of continuous functions, and by adding them, multiplying them, dividing them, we will be able to create a huge list of functions that we know are continuous. So let's get started. Well, this first theorem tells me how I can combine continuous functions. So if I have that f and g are continuous at c, then f plus g or f minus g are continuous at c. If I multiply a continuous function by a constant, that's still continuous. The product of continuous functions is continuous, and the quotient of continuous functions is continuous, provided that we're never divided by 0. But that's another issue. So each one of these follow immediately from the limit laws. I'm going to prove C, just to pick one, and I will leave the other ones for you as an exercise. Now, since we know that f and g are both continuous at c, we know that the limit as x approaches c of f of x is equal to f of c, and the limit as x approaches c of g of x is equal to g of c. Now, since both limits exist, we can use the limit laws that tells me that the limit of the product is the product of the limits. So the limit as x approaches c of f times g of x, which is the limit as x approaches c of f of x times g of x, is the limit as x approaches c of f of x times the limit as x approaches c of g of x. But that is f of c times g of c. But this is the function f times g of c. And that completes the proof. As you see, it was very easy and quick. We just had to invoke limit laws for limits of functions, and we just got things almost for free. Using these, we can, as I said, create many continuous functions. And a very nice example is that polynomials are continuous on R. How do we do that? Well, the main idea is that, well, first of all, we have a polynomial p of x, which is written as an times xn plus da da da, a1 x plus a0, and we're going to fix c to be any real number because we want to prove that it's continuous on R, so it has to be continuous for c, for every c in the real numbers. Okay, so it is easy to prove that the limit as x approaches c of x is c. That's very easy. I invite you to do it. You can do it, for example, using the definition or the characterization of limits via sequences. It's up to you. And also, we can easily see that the limit as x approaches c of the constant function x0 is equal to a0. Those two are very easy to do. I'll leave them for you as an exercise. But now, if we use part c, the one that tells me that the limit of the product is the product of the limits, and induction, then for any natural number k, the limit as x approaches c of x to the k is equal to the limit as x approaches c of x all the way to the k. But this is just c to the k. This induction proof, again, is extremely easy to do, so I invite you to give it a go. And now, once we have this, well, we're just going to combine. We'll have constants times x to the k. We have sums, so we're going to have multiples of continuous functions, sums of continuous functions. So the previous theorem is going to tell us that indeed any polynomial will be a continuous function. So how do we do that? Well, we need that the limit as x approaches c of p of x is just the limit as x approaches c of an xn plus dot 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 plus a1x plus a naught. But as we said, here we can use all these properties that we saw in the previous video to conclude that this limit is an times c to the n plus dot 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 a1 times c plus a naught, but this is indeed p of c. And that shows that indeed polynomials are continuous functions for any c in the real numbers. Excellent. So now that we have this, we can go a step further and look at another type of continuous functions. These rational functions. The rational functions are again continuous. So a function is a rational function if it is the quotient of two polynomials, and we need to ask that the polynomial in the denominator is not the constant function 0. It could be 0 at some points, and when the denominator becomes 0, we just say that the function is not defined. So that's something to keep in mind. So rational functions will be continuous everywhere on their domain. So they're going to be continuous at all points where the function is defined. If the function is not defined, then it cannot be continuous, of course. So you see, if f is defined at c, so that means that q of c is not 0, then the limit as x approaches c of f of x is the limit as x approaches c of p of x over q of x. But then this is using the main theorem that we saw in this video, just p of c over q of c, but this is just f of c. And that completes the proof of the fact that rational functions are continuous on their domain.